Welcome back to data mining. In this module, we will continue our quest to determine which patterns connect data inside of a dataset. Here, we will focus on covariance and correlation. In this module, we will learn how to define covariance and correlation and to pinpoint the connection between the two. We will learn how to determine when to use any of these, and then we will use covariance and correlation to analyze data in R and in Python. Both covariance and correlation are part of the measures of association. The measures of association answer the question, how is data related? There are different ways to analyze the relationships between data. We have here the measurements of independence. We're seeing covariance and correlation in that group, and another strategy, chi-square. Then we have the distance measurements here, namely the Euclidean distance, the Manhattan distance, and another type of distance, namely cosine similarity. Lastly, a third strategy of determining the relationship among data are measurements of comparison, namely regression, single and multiple regression, and ANOVA, the analysis of variance. Now here we are talking about bivariate or multivariate statistics. Measurements of association are typically a means of summarizing the size of the association between two variables. They are scaled so that their maximum value typically is 1 when the two variables have a perfect relationship. That relationship is typically positive, and a value of 0 when there is no relationship between the two variables. Some of these measurements don't just go from 0 to 1, but they have a range from -1 to +1, indicating either a positive relationship going towards +1 or an inverse, that is a negative relationship, if the measurement goes towards -1. But back to covariance and correlation. Let's start with covariance. We use covariance to find out how much two variables change together. This means we want to find out whether a change in one of the variables triggers a change in the other one, like whether a change in the hours you work, either an increase or a decrease, changes the amount of money you make. The important thing to remember is that covariance requires that the input attributes are at least somewhat close in unit or scale. Otherwise, the result doesn't make much sense. The results of covariance can lie between negative infinity and positive infinity. That can be hard to plot or manage. That's why we have correlation. Like covariance, correlation measures the strength and direction of a relationship, but it does that by standardizing the result of the associated covariance calculation. In other words, it takes covariance a step further by dividing the result of the covariance calculation between the two variables by the product of their standard deviations. And because standard deviation is the measure of how steep or flat the data distribution curve of a variable is, and because the area under the curve is always 1, the values we get from a correlation always lie between -1 and +1. To understand covariance in more detail, we have to look at variance first. Variance is related to just one single variable or attribute. It measures how far each value of that variable is from the mean of the same variable. Here's the formula. No worries, we'll walk through it. First, we find the mean, our x-bar. Then, we subtract that from all the values in our variable. That gives us the distance from each point to the mean. Then we square all those distances to make them positive and add them together. That gives us the sum of squares, which is nothing else than all the distances of all the values from the mean of the same variable. So it's usually a pretty big number. But because we are really looking for one single measure of variability here, we divide that sum of squares by the count or the frequency of the data points, and out comes the variance. Now, if you look closely, do you recognize that sigma? Right? That's the square of our standard deviation. And just like a large standard deviation shows a flat spread out curve and a small standard deviation shows a thin narrow spread of the data, that's also how the variance behaves. Here's an example based on the first 5 values in our income USD attribute from our adult data set. To find the variance, first we have to find the mean, that is the average. So we sum up all these values and we divide them by, we have 5 records here. That gives us this number. That is our mean. Then we calculate each one of these incomes difference from this mean. And then we square that difference. Then we sum all these squared differences. That gives us the sum of squares. Then we divide this sum of squares by the number of records. We've already decided that n is 5. And, oh, wait, we have to talk about something. Because we really are looking at a sample of our income USD data, namely the first 5 values. We are not looking at the population of all the values, namely the 32,000 and then some values. So we cannot divide by n. We have to divide by n minus 1. And that is the formula for when we are working with a sample and not the population. So we divide our sum of squares here by n minus 1, and we get our variance right here. Now, if we wanted to go a step further and figure out the standard deviation, all we would have to do is calculate the square root of the variance. That gives us this number. Awesome! The covariance of our data is calculated in a very similar fashion as the variance is calculated. So here we have a variable x, we have a variable y. We start out by determining the average, that's the mean of a variable x, and the average or the mean of a variable y. And then we go through all of the values in our variable x, and we subtract that mean from all the variables. And we do the same thing for our variable y, for our attribute y. Then, instead of taking the sum of squares, we now multiply the result that we get from this calculation with the result that we get from the same calculation for our second attribute. We sum that, and then we divide by either n if we are working with populations, or n minus 1 if we're working with samples from both attributes. That gives us the covariance. Now, a positive covariance means if our covariance is greater than 0, then x and y tend to be larger than their expected values, and our two attributes grow together. If we come out with a negative covariance, then if x is larger than its expected value, y is likely to be smaller than its expected value, which means we have an inverse relationship between those two attributes. So in other words, a positive covariance means that the variables are positively related, and a negative covariance means that the variables are inversely related. Here is an example of covariance. Now, let's say our buddy John is an investor and he looks at the S&P 500, which is the big market index, and he wants to determine whether he should buy the stock of ABC Corporation. So he wants to understand the relationship between how the stocks for ABC Corporation have been behaving in comparison to the S&P 500 values over the years. So we're looking at the years here, and we're taking just a subset, namely the values from 2013 to 2017. Here's our covariance formula. So the first thing we do, again, is we calculate the average prices for each asset, and then we subtract the mean from the original price, just like we did with the variance. So here we go, and here is the same calculation for ABC Corporation. So then instead of taking the sum of squares, though, we multiply this by this column, and then we sum our results here, and that's what we get. Now we could now divide the 36,429.2 by 5, but remember, we are working again just with a sample. We're not working with a population, which would be all the values from the beginning of the S&P 500 or from the beginning of when ABC Corporation stocks were traded to today. No, we have just these 5 numbers for these 5 years, right? So we cannot divide by 5. We have to use the formula for the sample, which means 5 minus 1. So here this n would have to be n minus 1. That gives us the covariance right here. This is a positive covariance, and that indicates that the price of the stock for ABC Corporation and the S&P 500 move in the same direction. So probably a good idea to purchase the stock of ABC Corporation. While covariance is a great way of determining how two variables behave in comparison with each other, it has a couple of problems, and we've seen that the numbers get quite large and we have to compare variables that have comparable units. Otherwise, our covariance is really not very meaningful. So in comes correlation. And here we're looking specifically at a Pearson's correlation, and the only difference that exists between a correlation formula and a covariance is really in the normalization that we're seeing here. The normalization, and here we're looking at the formula for the sample because we're seeing n minus 1. The normalization occurs by dividing our covariance, this is the covariance formula if you look very closely, by the standard deviation of our first variable multiplied by the standard deviation of our second variable. That gives us this formula here. This brings our correlation to a scale between -1 and +1. That allows us much more easily to compare different attributes of different units and different measurements, because everything is being reduced to this scale of -1 to +1. How our data behaves on that scale of -1 to +1 is what you're seeing here in this graphic. And you're seeing that a perfect relationship exists whenever we approach that 1. If it's -1, it is a perfectly inverse relationship. If we approach +1, it is a perfectly positive relationship. And the closer we get to 0, the less of a relationship among the data do we detect. In fact, 0 means there is no relationship among the data, and the data are all independent from each other. Because our correlation analysis allows us to normalize values, we can now compare attributes of different units. So here we're looking at a person's age or a patient's age here, and their glucose level. How do we do that? Well, let's calculate it by hand. Here we have the age, here we have the glucose level. The first thing we do is we calculate based on this formula here. We calculate the age squared. We calculate the glucose level squared. And we calculate the product of age and glucose level. Then we calculate the sums of each. Then we plug everything into the formula that we see up here. So we have, since we have 6 values here, and we assume that that is our entire data set that we have, 6 times our x times y minus, and then the sum of our age times the sum of our glucose, and we divide that by the square root of 6 times our x squared minus our x squared multiplied by 6 times our y squared minus our y squared, the sum here. And that gives us a correlation of 0.5298. So we are seeing that age and glucose level are positively related, not very much positively related, but enough positively related to say, well, there is a detectable relationship. So what do covariance and correlation look like in code? Let's first look at R. Here's what covariance looks like in R. We're looking at adult education years and adult income USD, which I have aliased here, so that the actual covariance formula looks a little bit cleaner. We just use COV on our 2 attributes here, and then we get our result. The problem here is that covariance is not normalized, which means we really are comparing apples and oranges or years and dollars. So the calculation here is not all that meaningful. If we want to find out how our education years attribute is related to our income USD attribute, the better way to calculate that relationship is by using correlation, since we're dealing with 2 different units, years versus dollars. So here again, I have cleaned up the variables by assigning little aliases to them, and then we're using COR instead of COV. COR gives us the correlation on our 2 attributes. We are using all observations, which also means that we're dividing by n and not by n minus 1. And then we have a number of correlation methods that we can use. Here we're using the Pearson's correlation. And that gives us our correlation here between our education years and our income USD, and we're seeing that our correlation here is 0.29, so about 0.3, and that is a pretty high number that indicates that there is a slightly positive correlation between education years and income USD. Not surprising. Now we can plot this correlation on a scatter plot, and we see here as well that our correlation, especially as we get to an education past year 10, becomes stronger and stronger. So here is our 0.29 in a graphic. And now let's see what correlation and covariance look like in Python. Here we're looking at the covariance calculations for our education years and our income USD attribute in our adult data set. And for each of these 4 different calculations, we're using our covariance function from the NumPy library. So the first calculation assumes that the data we're looking at is not the complete data, but it is a subset, a sample of all the data that exists. So this sets our degrees of freedom to 1, which means we're dividing not by n, but by n minus 1, if you remember the formula. So we're calculating our NumPy covariance on our attributes here, and this is our output. If we assume that the data that we're looking at, in contrast to our first calculation, is really all the data that exists, we are not working with sample data. We are now working with population data, which means that we set our degrees of freedom here to 0. That also means we're dividing by n and not by n minus 1. And that gives us this output here. Again, since we're working with a rather sizable data set with over 32,000 records, dividing by n versus dividing by n minus 1 really doesn't have that much of an impact, which is why we're seeing no difference between these numbers here. If we want to account for our values, for some of our values to be very high or very low, and we want to correct for this bias, we can here use the bias equals true setting. That will give us a slightly different output here. If we omit the bias equals true setting, we get back to our initial calculation here. Those are the different ways of calculating covariance in Python. To calculate the correlation between income USD and education years, we use the correlation function on our second attribute here, and we attach that to our first attribute. That gives us our correlation right here. And again, 0.29. That means, or almost 0.3, this means that we have a slightly strong positive correlation here. And then we can use pyplot here, plt.scatter, to build a scatter plot. And the scatter plot is shown here. The cool thing about correlation is that we can calculate that for multiple dimensions at the same time, as we're seeing here. If we just set up our adult.corr for any of our attributes against any of our attributes here, and we're seeing I have just 4 variables here in order to make this more readable. And we can make a pretty heat map here that shows us the correlation based on our correlation coefficient. -1 is blue, +1 is dark red, and of course each attribute is correlated to itself, the strongest with a 1. but then we're also seeing here the colors as they get darker based on the strength of the correlation. Very pretty. So in this module, we have looked at covariance and correlation. We have looked at when each one should be used. We have looked at the R code for correlation and covariance, and we've looked at the Python code for correlation and covariance. Awesome! Thank you so much for listening and watching, and I look forward to seeing you in a future module.